Good afternoon, everyone. Today is lecture number 21 of this heat treatment lecture. And today's menus are like this: iron chromium phase diagram, showing the effect of chromium on different phases of iron. Here, basically, we will discuss about this uh, the stabilization of the ferrite phase due to addition of chromium, because chromium, basically, you understand, is an alloying element which stabilizes the ferrite, BCC, but unstabilize the austenite phase, FCC. And also we'll see the effect of alloying elements on iron carbon phase diagram, right? So basically here we'll discuss about what happens to these A3 points, that is the upper critical temperature, and what happens to the eutectoid temperature also, with addition of different alloying elements. Then problems with martensitic stainless steel. And so in the previous lecture, we have discussed about what happens, what are the problems associated with the austenitic stainless steels. If you remember the different problems. And also we have discussed about the problems associated with the stainless steel containing some chromium and all, right? Then finally, we'll discuss about Maraging steel, which is basically an ultra high strength steel. This is one of the important steel we have. It found applications in many like aircrafts and defense applications also it has. So this is you can see iron chromium phase diagram. So phase diagram, you people understand. Phase diagram means temperature versus composition. So this is the temperature axis and this is the composition axis. And if you remember, in one end it is iron and this end is the chromium. So it is 100% iron and this end is the 100% chromium, right? And see, here we are varying the weight percentage of chromium in this direction. We are increasing the weight percentage of chromium starting from 0 to 100%, right? So what happened to the, and if you remember, iron have different allotropic forms, that is delta ferrite, gamma and alpha, and liquid phase at high temperature. So liquid, then delta, then gamma, then alpha, right? But you can see with addition of chromium what is happening to these things. So what are the observation we can see? The first observation we can see is, as we know, this chromium is a ferrite stabilizer. It stabilizes the ferrite phase. That means it stabilizes the BCC structure. But in other words, in other way, I can say it unstabilizes the austenite phase, or it unstabilizes the FCC. That is gamma here, right? So first observation is, I can see formation of gamma loop, showing separation of austenite and ferrite. So gamma loop is here. You can see there is a gamma loop, right? So this gamma loop is showing separation of austenite phase and ferrite phase here, right? Gamma loop is separating the austenite and ferrite phase. So it's the first observation. And if you remember how the gamma loop forms, the gamma loop basically forms when the percentage of ferrite stabilizer is more in the steels. Right here, here chromium is the ferrite stabilizer. So when increasing in the ferrite stabilizer, what happens? If you remember, the A3 point will go up, right, and A4 point will come down, and they will merge after if the chromium percent is very high. Right, complete elimination of austenite phase may happen. Here in this region, you can see there is no austenite phase here. Only ferrite is there. That means starting from the room temperature to the high temperature, ferrite we have. So this is first one. Second one, you can see formation of intermetallic sigma phase. Here the sigma is there. In iron chromium phase diagram, we have a intermetallic phase, that is sigma. And this is the formula of that. Chromium 4, iron chromium 16, iron 10. Right? Intermetallic phase. And this phase is what? Basically, this phase forms very slowly, and this is a brittle in nature. Right? So if we have a stainless steel, basically, because chromium is the major alloying element in stainless steels, that is above 11.5 or 12 percentage. So sometimes what happens, this kind of brittle phase like sigma phase may form at certain temperature, which reduces the toughness or fracture toughness of the material of this stainless steel. Which basically
Yes,
may happens.
Gandhi,
Yes,
it's a question to join.
this may happens when we have martensitic stainless steels, when we have ferritic stainless steels, when we have these uh, dual phase stainless steel. And this is third one. This is third. So what is another observation? At low temperature, ferrite field is separated into, or it decomposed into two alpha and alpha prime phase. You can see at high temperature, solubility is more, right? Chromium is more soluble in iron at high temperature, and iron is more soluble in chromium at high temperature, right? So they are forming a solid solution, single phase solid solution, alpha. But the moment the temperature is going down, you can see we have two phases, alpha and alpha prime. Or if you are writing alpha prime, you can write alpha double prime here, no problem. The difference may be the similarity. You understand what is the similarity? It is alpha, it is alpha, it is alpha. Similarity is what? Similarity is they have same crystal structure, BCC, suppose, or right. So the structure here, the crystal structure here and here are same, but the composition is different. The composition here is different from here and different from here. That's all. So these are the three observations you can see. First, the formation of gamma loop, which is separating austenite and ferrite. Second, we can see formation of an intermetallic compound, which is sigma, which is basically brittle in nature. And another one is the single phase alpha decomposed into two phase, alpha and alpha prime at low temperature. These are the observations you can have. If you have gone through the phase transformation class, you might have heard about this miscibility gap. This part is called miscibility gap, if you remember. And which occurs at a low temperature, basically. There is a minimum temperature where there is a miscibility gap. There will be no solubility. And also you have heard about spinodal decomposition, I think. I'm sure you have heard about this spinodal decomposition, which occurs due to this miscibility gap. Okay, fine. You got the conclusion. The conclusion here, main conclusion is what exactly? If we increase chromium percentage in iron, the gamma phase is destabilized, but alpha phase is getting stabilized. And another important point is we are getting a intermetallic compound at low temperature due to decrease in the solubility.
Hello, sir.
Yes.
Sir, see previous diagram रे carbon तो absent अच्छी तो sir without carbon strength केमती आसे sir?
Yes. Sorry. Can you tell me what? Can you repeat your question?
Sir ए diagram sir carbon absent अच्छी तो without carbon strength केमती आसे sir?
Without carbon strength केमती आसी iron रे?
Yes sir.
Yes, it is. You understand when chromium is added to the iron, it is forming a solid solution. So it is solid solution strengthening will be there. And as I told, a sigma phase is forming. It is a brittle phase. So it gives some strength also.
Okay sir.
You understand now? But basically,
Yes
if you
sir.
look into if you're talking about the steel, then carbon will be there, right? Some amount of carbon will be there. It depends upon low carbon or medium carbon, like that. But here we are only talking about iron and chromium. This picture is basically to show you the effect of chromium on iron. What is getting stabilized and what is getting unstabilized. Here alpha phase is getting stabilized. Gamma phase is getting unstabilized, due to which a loop of gamma is forming. You understand my point? You are here, alpha is there, right? Here gamma should be present here, right? At high temperature. Because gamma is a stable phase at a high temperature for iron. Alpha is a stable phase at a low temperature. but still you can see the room is very high. Here gamma should be there, but here alpha is there due to addition of chromium. Chromium is a ferrite stabilizer. Okay, fine. So now we have three images. You can see the first image is effect of chromium on austenite phase. So you understand this dotted part is nothing but the austenite phase. You people are figuring, just figure it out. This is an austenite phase only. That means I'm talking about iron carbon phase diagram, and I have only taken the austenite phase, austenitic region, right? It is okay. So this dotted part is austenite region. You can see so our austenite phase is bigger phase region. Everybody know, right? Let me show you if you have forgotten. This one, I'm talking about this region, right? You can see this region, austenite region is a very big region in iron carbon phase diagram, which is shown over here. This one, this dotted line, fine. So now you can see what will happen if we add chromium into this iron carbon phase diagram, or what will happen when we add chromium into this steel. What will happen to this phase, austenite phase? So initially this dotted part is showing 0% chromium. Now you can see this part from here to here. This is 5% chromium, I can say. Yeah, 5% chromium. So that means when chromium is 0, the gamma region is bigger, this one. But when I add 5% chromium, the gamma region is decreasing, right? It is okay. Then further, when I add 12% chromium, so this is my region. The region is getting smaller and smaller. Then when I add 19%, sorry, 15%, so this is the region, gamma region, small triangle here. And finally, when chromium is 19%, the gamma region is this one, this small triangle, the crusher, you can see. So conclusion is what? The conclusion is simple. Chromium is a ferrite stabilizer. It stabilizes the ferrite. It increases the region of alpha, or it increases the region of BCC, but it destabilizes the gamma phase. It destabilizes the austenite phase, right? So that's why what happens with increasing in the percentage of chromium from 15 to 20, 12 to, 5 to 12 to 15 to 19. So you can see this is a small region of gamma left over here, right? And also you can see this, suppose this is your A4 line, it is decreasing. And this is your, suppose, A3 line, this one, right? A3 line is increasing up, or I can say A3 point will go up, A4 point will go down. It is okay now. Next is this one, effect of alloying elements on eutectoid temperature. You people understood eutectoid temperature is the temperature above which austenite start forming. If it is an eutectoid still, then 100% austenite will form above the eutectoid temperature, right? So you understand. Now the question is what happens if we add alloying elements? Then what happened to the eutectoid temperature, right? You can call A1 temperature simply. Eutectoid temperature is nothing but the A1, lower critical temperature, right? So you can see titanium effect. When we are adding titanium, it is moving up. When we are adding molybdenum, it is moving up. When we are adding tungsten, it is moving up. When we are adding silicon, it is moving up. When we are adding chromium, it is moving like this. But the moment I am adding manganese, the eutectoid temperature is going down. You can see like this. When I add nickel, the eutectoid temperature is going down. So can you people figure it out what is happening due to addition of alloying element? What happens to the eutectoid temperature when we add different alloying elements? Hmm? Can you figure it out quickly?
Sir, manganese and
I am
nickel is
talking about this
Austen.
temperature, right? I am talking about this temperature, this one, A1 temperature, lower critical temperature. This temperature is going up sometimes, and this temperature is going down with different alloying elements. Yeah, yeah. Someone is saying Somya. Yeah, Somya, you can speak. Yes, Somya, you can speak.
Sir, manganese and nickel is austenity stabilizer.
Very good.
So when we add it,
Mm-hmm.
temperature decreases
Yes.
on austenitic region increases when we adding manganese and nickel.
Mm-hmm.
Sir, but chromium, tungsten, silicon, that is ferrite stabilizer.
Mm-hmm.
So when we add it, it increases ferritic region so that A1 temperature increases.
Yes, very good, very good. Well explained. So people understood, right? He is exactly true. You can see titanium, molybdenum, silicon, tungsten, chromium, all are ferritic stabilizer. They stabilizes the ferrite phase. And you understand below A1 temperature, this one, if you can recall, this temperature, this is the A1 temperature, lower critical temperature. Below this, ferrite is stable phase, and above this, austenite is the stable phase, right? So that means if we add more amount of ferrite stabilizer, what will happen to this eutectoid temperature? It will go up. Obviously, why? Because it wants to stabilize the ferrite phase. So ferrite region will increase if this A1 line will go up, right? So similarly, you can see with addition of nickel and manganese. Nickel and manganese are one of the important example of austenite stabilizer. They stabilizes the austenite phase, right? So if they want to stabilize the austenite phase, that means the austenite region will grow up. It will become more bigger region. It will occupy more bigger region. So what will happen? This this A1 or this eutectoid temperature will go down, right? So this is the effect of alloying element on eutectoid temperature. So eutectoid temperature will go up or it will rise if you add ferritic stabilizer. If you add austenitic stabilizer, the eutectoid temperature will go down. And it is pronounced, you can see it is titanium, molybdenum, basically shows more rise in the eutectoid temperature. Basically, titanium has more effect. Right? So this is the last image we have. This is showing effect of carbon content of the eutectoid composition. You understand eutectoid composition, the carbon weight percentage 0.8 or 0.77 weight percentage. So what will happen to the eutectoid carbon composition? Effect of carbon content of the eutectoid composition. That is, if we add alloying elements. So you can see if even if you are adding many alloying elements, what is happening? It will decreases the carbon content of the eutectoid composition. For every alloying elements, it is going down. You can see whether it is carbon, manganese, nickel, titanium, molybdenum, right? So that in other words, I can say it may be an austenite stabilizer, it may be a ferrite stabilizer. The carbon percentage basically decreases of the eutectoid composition. So, okay. Now the next topic is problems with martensitic stainless steels. So if there are basically two problems with martensitic stainless steels. First problem is precipitation of carbides occurs along grain boundaries. So due to precipitation of carbides along grain boundaries, what will happen? The corrosion resistance decreases and the ductility decreases. So these are the problems. And the second issue we have written austenite. We have a written austenite. You understand written austenite is very soft phase, and further if it getting transformed into some other phases, there will be a volume change, and volume change leads to what? Generation of residual stresses in the steel. So that's why it will require always sub-zero treatment. After formation of martensite, we can go for sub-zero treatment to remove this written austenite so that it will transform into martensite. Hmm. And you understand why written austenite is there because of nickel and carbon. Nickel and carbon are austenite stabilizers basically, right? Carbon is a austenite stabilizer, nickel is also austenite stabilizer. So you people are getting the point now why high carbon steels have more written austenite. because carbon is a austenite stabilizer. So that is one of the point. It try to stabilize the austenite phase. So that means it will decreases what? Eutectoid temperature, obviously. So carbon also decreases the eutectoid temperature. That means, right? Nickel also decreases the eutectoid temperature, and the A3 point also goes down. You understand? Maraging steels. Okay, fine. So there was a topic as we have already discussed, that is different type of steels, but we have left with this one, maraging steels, which is an important class of steels because these are ultra high strength steels. They have wide applications in defense applications, in aerospace applications or aircraft applications. So you can see the interesting point is property. You can see the property. It has good formability, weldability, high strength, high yield, strength to tensile strength ratio, high fracture toughness. These are very interesting point about. So that means maraging steels have high strength also and high fracture toughness also. They can be easily weldable. They have good formability also. Hmm. And these kind of steels have lot of alloying elements basically. So that's why its hardenability is very high. Hardenability is very high means martensite forms on air cooling. That means martensite will easily form if we are doing air cooling. We do not have to go for quenching or severe rate of cooling. So just by doing air cooling, we can generate martensite in this structure because of high alloying additions in it. Then what are the alloying elements in maraging steels? Obviously, it is a steel means iron will be there, but other important element is the nickel. Hmm. And what are other alloying elements? We can have titanium, beryllium, aluminum, niobium, tungsten, molybdenum, cobalt. So we can have variety of maraging steels, but these are the major alloying elements or different alloying elements present in it. And you have to remember, this is an interesting point here. Weight percentage of carbon in this steel is kept below 0.03, very low. So these are very low carbon steels. Weight percentage of carbon is very low, 0.03. It should not be exist than 0.03. Okay, how many of you remember what happened to the strength of martensite if we increase the weight percentage of carbon? What happened to the strength of the martensite if we increase the weight percentage of carbon in steel?
Increase.
Yes, very good. It basically increases, but it goes to a saturation limit. But basically, it increases. Uh, so it increases. You understand, because the carbon will occupy the octahedral voids. So once it will occupy, and these octahedral voids are present in which part of the BCT? It is present in the edge, right? Center of the edge. Hmm. So center of the edge of the BCT it is there, and due to martensitic transformation, the C axis try to shrink, right? The C axis will try to shrink, but due to presence of this carbon always what provides compression field, right? It push the iron outwards, right? So the shrinking will be very difficult. During martensitic transformation, the C axis want to shrink, but due to presence of this carbon at the center of the edge of the BCT, there will be no shrinkage. All the shrinkage will be very minimum. So obviously strength will be very high. That is called tetragonality, if you remember. In the previous class we have discussed in previous lectures. Yes. So now martensite from form in the steel is carbon free. You can say yes. Why? Because the weight percentage of carbon in maraging steel is very low. That is less than 0.03. So you can call the martensite form is a carbonless martensite. And you understand, once it is a carbonless martensite, it is a ductile one, tougher one, but it is not having high strength, right? So here it is written: iron nickel martensite is soft by nature. They have low strength, but high ductility. Can you people tell me, can we produce martensite upon rapid quenching of a pure iron from FCC structure? Is it possible? Can we produce martensite in a pure iron? We have a pure iron, and my iron is now at high temperature, that is FCC structure. Now you quench it. So can you produce a martensite? The answer is yes. The definition of martensite basically we called is, it is a supersaturated solid solution of carbon in BCC iron, and its crystal structure is BCT. But this is one of the definition, but this is not the true definition of martensite, because martensite is a non-equilibrium structure, right? Non-equilibrium microstructure which forms due to non-equilibrium cooling. But whenever we have a martensitic transformation, two things always happens. One is the shear. Shear means there will be a plastic deformation will happen, right? Only the parent lattice will get deformed, plastically there is a plastic deformation will happen, right? That is called shear, right? And another thing will happen, there is a volume change. The C axis will try to shrink, the A and B axis will try to expand. So these two things happens. If two things is happening, that is change in volume and there is a shear or there is a plastic deformation, then that it is a martensitic transformation simply. So carbon will be there or it will be not there in iron, then we can also form a martensite. But if somebody will ask what is the difference, the difference is what? The pure iron, the martensite form is a very soft martensite. It is a soft martensite. It is not a very hard martensite. But the martensite which forms in steel having carbon, more and more carbon, it is more harder and more stronger. Next is, you can see microstructure. So what is the microstructure of maraging steels? You understand. You have to remember, this is a very important part. Maraging steel. Maraging steel. Steel, you understand, iron will be there obviously. And here nickel is also there, as I told, 18% nickel, right? So that form a matrix phase, right? That is the matrix we can say. Maraging. Mar for martensite. Aging means formation of precipitates due to aging heat treatment. It is okay? Maraging. Mar means martensite. Aging means there is an aging process which generate precipitates. Basically, intermetallic compounds will form, which are the precipitate phase on the matrix. So microstructure is a soft martensite matrix having precipitates of intermetallic compounds. You people understood why it is a soft martensitic matrix? Because due to less amount of carbon. The carbon percent is very low, below 0.038%. Or carbon-free martensite. It is an iron nickel martensite, simply. Okay, what are the main type of precipitates we can have? Ni3MO, Ni3Ti, because these are the alloying elements, they are forming intermetallic compounds between different elements. Ni3MO, Ni3Ti, Ni3Al, Fe2MO, which occurs in a volume fraction because of high alloying content. Carbide precipitation is suppressed. There will be no formation of carbides basically. Instead of carbide formation, we have intermetallic compounds. Because carbon percentage is very low, so carbide formation will be suppressed. And now important question is generalized heat treatment cycle. So you understand, you have to form martensite in this steel and you have to form precipitates in this steel. But these precipitates are basically intermetallic precipitates. You can see these are intermetallic compounds. Compound between two metals, basically. So you understand, if you want to form martensite, then and you have a lot of alloying elements. So the process is what? Solutionizing, right? So you have to take the steel to a very high temperature where we have a single phase only. Suppose here for steel, it is an austenite phase. Single austenite phase will be there. Every alloying elements or every precipitates, earlier precipitates we have will get soluble in the austenite phase. Then we quench it from that temperature. From the austenitizing temperature, we have to quench it. all the alloying element will remain in solid solution. So it is a solutionizing heat treatment. So after that, so this is the temperature, 820 degrees centigrade. And time is 1 hour, basically. Then after that, what we have to do? We have to reheat the steel. That is called aging temperature. That is 480 degrees centigrade for 3 hours. So due to this aging heat treatment, we will have these kind of precipitates. We will have these kind of intermetallic compounds. So martensite, soft martensite matrix will be having this kind of intermetallic compounds. These intermetallic compounds are very strong. They prevent the motion of dislocation. That will give rise to precipitation strengthening. You understand? So in a single statement, I can say, Maraging steels, the strengthening is due to transformation strengthening plus precipitation strengthening. Transformation strengthening will come due to transformation of the austenite phase to the martensite phase. Right? Martensite is a very hard, basically, but steel it is not so hard. It is ductile one, so it provides good toughness actually. Here martensite is providing good toughness, and the precipitates will provide you very high strength. That is precipitation strengthening, right? If you remember, application is one of the application aircraft components. A defense purpose we are using this one. There is a question, function of cobalt. If we have cobalt addition in maraging steels, what is the function of cobalt? So one of the function is it reduces the solubility limit of molybdenum. So if the solubility limit of molybdenum will decrease, that means molybdenum will be not soluble. It will not form solid solution. It will form precipitate. So molybdenum rich precipitate will form, right? Then cobalt also helps in the uniform dispersion of precipitates. The precipitate will uniformly distributed everywhere in the martensitic matrix. Then last one is cobalt accelerates the precipitation process. The precipitation process will be getting accelerated if cobalt will be there. So thereby shortens the aging time. The aging time will be reduced. These are the things. Okay, so I want to close this topic. We'll continue our lecture from the next class.